In this PowerPoint, we are going to discuss about two concepts. First one will be electronic configuration and the second one will be valency. You know that the atom consists of a central nucleus and electrons revolving around it. Electronic configuration of atom describes how these electrons are distributed in its atomic orbitals. There are certain rules to fill these electrons in the orbitals. So let's see what are the rules to write electronic configuration of an atom. As you can see, the first rule says that the maximum number of electrons that can be accommodated by an orbit is given by the formula 2n square, where n indicates the number of the orbital. Now let's check the table. You can see that K shell is the first shell, therefore n is assigned the value of 1. L is the second shell, therefore n is equal to 2. M is the third shell, therefore n is equal to 3. N is the fourth shell, therefore n becomes 4. Now, if we calculate the maximum number of electrons in the first shell by applying the formula 2 into n square and by assigning the value of n as 1, we get 2 into 1 square is equal to 2. That means the maximum number of electrons that can be accommodated in the K shell is 2. Similarly, by applying the formula 2n square and by assigning the values of n as 2, 3 and 4 in the second, third and fourth shells respectively, we get the maximum number of electrons that can be accommodated in the L shell is 8, in M shell it will be 18 and in the N shell it will be 32. Now moving on to the second rule. The second rule says that the electrons in these shells should be filled in a stepwise manner. That means only after filling the first shell completely we move on to the second shell and third shell and so on. The third rule says that the maximum number of electrons that can be accommodated in the outermost shell, that is the valence shell, should not be more than 8 electrons. Here in this table, electronic configuration of elements of atomic number 1 to 20 has been given. So randomly, let's analyze electronic configuration of few elements and verify the rules already discussed in previous slide. Here, the first element is hydrogen with atomic number 1, hence number of electrons is also 1. According to the rule, electrons are filled in stepwise manner. Therefore, the 1 electron of hydrogen atom occupies the first shell, that is the K shell. The second element is helium. It has 2 electrons and both the electrons are occupied in the first shell itself. Third element is lithium. It has 3 electrons. The first 2 electrons get filled in the first shell and the third electron occupies the second shell. Now, why is it so? So, here you have to recall that the maximum number of electrons that can be accommodated in the first shell is 2. In case of lithium, first shell is completely filled as it have already 2 electrons. So, the third electron goes to the second shell. If you check the electronic configuration from beryllium to neon, you can see that since first shell is completely filled in all these atoms, all the extra electrons which are entering are in the second shell, that is the L shell. Now coming down to sodium, the electronic configuration of sodium is 281. The 11 electrons of sodium are distributed among 3 shells K, L and M respectively. In case of sodium, K shell is completely filled with 2 electrons. So the electron enter the second shell, that is the L shell. By rule, the maximum number of electrons accommodated by the second shell is 8. Hence, second shell of sodium is also completely filled. Therefore, the 11th electron goes to the third shell. So the electronic configuration of sodium becomes 2, 8 and 1. Now let's check the electronic configuration of potassium. It's 2881. As per rule, first and second shell of potassium are completely filled with 2 and 8 electrons respectively. So now the remaining 9 electrons should enter the third shell, as the third shell can accommodate maximum 18 electrons as per the formula 2n square. But here you can see third shell is having 8 electrons and remaining 1 electron goes to the fourth shell. Now to answer this, we need to recall the rule that maximum number of electrons that can be accommodated in the outermost orbit of an atom should not exceed than 8 electrons. Therefore, from the remaining 9 electrons,
the 8 electrons enter the third shell and the remaining 1 electron goes to the fourth shell. And therefore the electronic configuration of potassium becomes 2881. We know that most of the atoms do not exist independently. It combines with other atoms to form molecules and compounds. So why does atom cannot exist independently? The reason for this is most of the atoms are not stable as they do not possess the stable configuration. In order to explain stable configuration, we need to recall octet rule. The rule states that every atom tends to achieve 8 electrons in its outermost shell. In order to clarify the rule better, let's examine the table given below. Here, 5 noble gases are listed: helium, neon, argon, krypton, and xenon. If we analyze the electronic configuration of all these atoms, we can see that all the orbital of these elements are completely filled and have 8 electrons in their outermost shell except helium. These elements are observed to be highly stable and can exist independently as atom, and that is why noble gases are found to be monoatomic. Atoms tends to achieve this stable electronic configuration of noble gases by gaining, losing, or sharing electrons.
In previous slide, you learned that atoms try to achieve the stable electronic configuration of noble gases. So let's see how this is done. But before that, let's examine the tables given here. Inside yellow table, some elements which are metals and its electronic configuration are listed. Red table consists of noble gases and its electronic configuration, and blue table have some elements which are non-metals and its electronic configuration. So first let's examine the yellow table. Lithium having atomic number 3, electronic configuration 2, 1. Lithium does not have 8 electrons in its outermost shell and hence it is not stable. It will try to attain the stability by achieving the stable electronic configuration of the nearest noble gas. So how lithium is going to achieve that? Electronic configuration of lithium is 2, 1. Here, either lithium can lose one electron. When it loses one electron, its electronic configuration becomes 2, which is same as that of the electronic configuration of helium. Or it can gain 7 more electrons in its outermost shell and achieve the electronic configuration of 2H, which is same as that of the electronic configuration of neon. But in case of lithium, losing one electron is more easier than gaining 7 more electrons to achieve the stable configuration. Therefore, lithium loses its one electron to achieve the stable configuration of its nearest noble gas, helium. Similarly, in case of aluminium, either it can lose 3 electrons and attain the stable configuration of neon, or gain 4 more electrons and attain the stable configuration of argon. Since losing 3 electrons is more easier than gaining 4 more electrons, aluminium achieves its stable configuration of neon by losing 3 electrons from its outermost shell. Similarly, if we analyze the rest of the elements in this table, we can see that these elements achieve stable configuration of its nearest noble gas by losing electrons present in its outermost shell. Now, moving on towards the blue table, oxygen having electronic configuration 2, 6. Oxygen can either gain 2 electrons and achieve the stable electronic configuration of 2, 8 as that of argon, or it can lose 6 electrons and achieve the electronic configuration of 2 as that of helium. In case of oxygen, it is more easier to gain 2 electrons than losing 6 electrons to achieve the stable electronic configuration. Hence, oxygen gains 2 electrons and attains the electronic configuration of neon. Now if we examine the case of chlorine, chlorine either can gain 1 electron and attain the electronic configuration of argon, or lose 7 electrons and attain stable electronic configuration of neon. Since gaining 1 electron is more easier than losing 7 electrons, chlorine achieves stable configuration of argon by gaining 1 electron in its outermost shell. Similarly, if we analyze the other elements in this table, we can see that these elements achieve stable electronic configuration of its nearest noble gas by gaining electrons required to form octet, that is 8 electrons in its outermost shell. By now you have understood that atoms attain stable configuration by gaining, losing or sharing of electrons. The number of electrons that are gained, lost or shared gives us the valency of that element, that is combining capacity of an element. There are two simple ways to determine the valency of an element. One, if the number of valence electrons, by valence electrons we mean the number of electrons present in the outermost shell. So if the number of valence electrons is less than or equal to 4, then the valency of that atom is equal to the valence electrons. That is, valency of the atom in such cases is equal to the number of electrons present in its outermost shell. For example, if we take magnesium, magnesium has electronic configuration 282. Magnesium easily loses 2 electrons to attain the stable electronic configuration. Therefore, the valency of magnesium is 2, that is the number of electrons present in its outermost shell. Now, the second way to determine the valency is, if the number of valence electrons is greater than 4, then the valency is determined by subtracting the valence electrons from 8. For example, sulfur has electronic configuration 286. The outermost shell of sulfur has 6 electrons, that is, sulfur has 6 valence electrons, which is greater than 4. So in case of sulfur, valency can be calculated by subtracting the valence electrons of sulfur from 8, that is 8 minus 6 gives 2, that is valency of sulfur is 2. Let's analyze this table containing valency of elements from atomic number 1 to 20. Here you can see helium, neon and argon are having valency 0 because they are having stable electronic configuration and hence their combining capacity becomes 0. You can analyze and verify the valency of the rest of the elements in this table using two methods learnt in the previous slide. Hope you have understood the method to write electronic configuration and to determine the valency of an element. Thank you, children.